So this over here. We just took our test. I still have a couple of people who need to take it, so we'll get that back next Tuesday. But we're going to be plodding along in chapter 3. So I'm going to assign a homework on Top Hat. And that will be due next Thursday. And then my intention was to make your guided notes due the same day, but apparently on Canvas, I put it for the 7th instead of the 6th. But if you want to turn it in class on the 6th, that's fine too. So your guided notes, we'll finish almost all of them today. We just have a few things to do next Tuesday. This is going to be done on Canvas. Canvas isn't done. So those are the things that are coming up. And then today we will wrap up our thing with rock candy and get that turned in. So any questions about stuff that's going on? So I think what I'm going to do is I'm going to start with looking at the guided notes. If you pull these out, I'm going to go through a couple of PowerPoints and practice some things with concentration. So we already talked about the mole. I'm going to go through those slides really quickly as a review, and then we will look at how to calculate concentration. So, oh, one thing on the guided notes on Canvas, I haven't put the link to this sheet. The questions are pretty similar, but what I want is this sheet. It's easier if you're all on the same piece of paper. It's harder to grade when everything is on different pages. So I'll put a link to this if you want to like have that online in a digital form to turn in. That's perfectly fine. But handwritten is also good. Okay, where was I? Move this bar so I can see. Wait for the computer to warm up. My husband gave me this word a day calendar, and earlier this week there was one that I thought was appropriate to this class. Anybody here taking Japanese? Okay. I don't know how to pronounce things in Japanese, so I'm going to say it's zatsumi. This is a word used in Japan to describe an undesirable flavor, usually in sake, which is the alcoholic beverage that people in Japan usually drink. It doesn't refer to any particular bad flavor. The word even translates to miscellaneous taste in English. So the next time you taste something funky in the leftovers that have been sitting in your fridge all week, just call it zatsumi and don't think about it too hard. So I thought that was appropriate for our class. Zatsumi. Okay, so as I said, we're just going to do a little bit of review here. I'm going to go through this pretty quickly because we already talked about this. So the moles, this is that number, 6.022 times 10 to the 23rd. And we looked at that being a very, very large number. So more than the number of stars in the sky. So the reason we use it is because it's better at keeping the atom ratio than masses. Because if I try to use the mass of an atom, the mass is too tiny to weigh out individual things, first of all. So I have to have like at least a milligram of something, and that's already getting to be lots of atoms. And also we have atoms that weigh 1, like hydrogen, and atoms that weigh 207, like lead. So when I'm talking about how concentrated they are, if I have one of each, then that's a 1-to-1 ratio, but the mass ratio is very, very different. So we have different ways of doing concentration that we'll talk about. Okay, we won't ever really use this number, but it does come up in chemistry classes. I'm like legally obligated to show you the number if I teach chemistry. So we talked about if we have a mole of something, and so I've got my picture of a mole here. A mole of something has this many particles. So a mole has this many water molecules. If I have a mole of water molecules, I'm going to have 2 moles of hydrogen because there's a little 2 here. That's what that subscript means. There's 2 for every one of the whole thing. And I have 1 mole of oxygen. All right. I think this is a picture of mole, which is also spelled M-O-L-E. So that's why that picture's there. So if we look at the periodic table, the elements on the periodic table have the number that is the number of protons, that's their atomic number, but then they also have one with a decimal, and that decimal is the mass, the molar mass. So when I look at nitrogen, it says nitrogen is 14.01. And that just means if I have 6.022 times 10 to the 23rd atoms of nitrogen, or 1 mole of nitrogen, that's how much it would weigh. So our units there are grams per mole. But if I have a diatomic, I use the same word both for the atom, nitrogen, and for the molecule, nitrogen. So if I had a mole of nitrogen molecules, since each molecule has 2 nitrogens, it's twice as much. So 28 is twice what 14 is. Okay, so we talked a little bit about calculating molar mass. I had you do a little small calculation of molar mass on your test. Hopefully that wasn't too scary. All right. So I put calculators at your desks. So there should be at least one available to you. So one person's going to grab that calculator and they're going to calculate the molar mass of carbon monoxide. So other people help that person find what is the mass of carbon, what is the mass of oxygen, so those two can be added together. Carbon should be about 12. Oxygen should be about 16. Anybody got a number yet?
28.01.
28.01. I would agree with that. Okay, now pass that calculator to somebody else. Somebody else is going to look at hydrogen, but you have to count hydrogen twice, and sulfur once. So sulfur is right below oxygen on the periodic table. All right, somebody from this side of the room over here. What'd you get?
34.076.
That sounds about right. So we have some numbers and some periodic tables. We have just 2 numbers after the decimal. Sometimes we'll have 4 numbers after the decimal. So it varies from element to element. So you may have gotten that 0, 7, whatever from the sulfur, and then depending on how many you had from the hydrogen, that might have made it a little bit smaller. But if you just used 1.01 for the hydrogen, then maybe you rounded it to 34.08. So they can be slightly off. That last digit should be the place where we have some differences. All right. Okay. Who just walked in? Or that was somebody just grabbing something. Okay. All right. Pass it off to another person or back to the first person, depending on who's there. Now we have C12H22O11. So this is the chemical formula for sugar, the very same chemical that we dissolved in water this time last week. All right, so we had people from the front of the room giving us answers last time. So somebody from the back of the room, when you have an answer, let us know what that mass is. 342-ish? Yeah. So I rounded that one because we had 3 sig figs on the other side and having the other. I don't remember what this next chemical is. I'll have to look up what that one's supposed to be, but that's a pretty big one. That one is 386. That's a pretty big molecule. I bet that's like a fatty acid or something. All right, so now let's try this one. You'll have to either share the calculator or share your information. This is one of the monomers of sucrose. So sucrose is made up of 2 monosaccharides. And this one, actually, they all have the same formula, but I'm thinking of glucose. You've probably heard of glucose. We sometimes call it blood sugar. So what is the molar mass of that one? See what we got here. All right. So it should be right around 180. So we have 6 carbons, each are 12, so 12 times 6. 12 hydrogens, so 12 times 1.01, and 6 oxygens, each of which are 16, so 6 times 16, and add those all. Okay, so we talked about some molecules that you should know. So you should know which ones are diatomic. They're listed here. And then there are some compounds that we just use all the time. I'm sure you all know water is H2O. CO2 is carbon dioxide. That's a common product when we're reacting things. It's evolved when you are fermenting things, when you're making bread, and also when you burn things. This one, CH4, methane, is what is in natural gas. So if you're cooking over a stove that has natural gas, almost all of what's in there is methane. So that's a good one to know. And then this one we'll talk a little bit more about in other chapters. This is ethanol. And you'll see that the hydrogens are in 3 places. That's to illustrate what the molecule looks like. So you have a carbon with 3 hydrogens, then a carbon with 2 hydrogens, then an oxygen with an H. But we could put those all together and just say C2H6O. That would be fine as well. But you should know the formula for ethanol. And then the one that we just did was glucose. You should recognize that one as well. All right. What we didn't talk about was how to find moles from mass or mass from moles. So if I know how much mass I have, say what the weight of the sugar that I put into my beaker last week was, I can figure out how many moles, which is in turn is kind of telling me how many molecules that I have there. So what I'm going to do is I'm going to say the molar weight is the mass divided by moles. I can rearrange that to find the number of moles. So I'm going to write this on the board real quick. Here we go. So molar weight is mass over moles. And if we're trying to find moles from algebra, we do unto one side as we do unto the other. So I'm going to multiply both sides by moles. That side's going to cancel out. Now my mass is going to be molar weight times moles. But I want moles by itself, so I'm going to divide both sides by the molar weight. So moles is equal to mass over molar weight. Okay, so if I know what the mass of something is, I just divide by the mass by the molar weight. So for water, water's molar mass is 18.02 grams per mole. I get that from 16 for oxygen, 1 for each hydrogen. Okay. And if I want to know how many moles are in 250 grams, then I'm just going to say 250 divided by that 18.02. So there's finding the molar mass. Then I divide it, and that we say we have 13.9 moles of water. Okay, so that's an example of how to calculate that. All right, so if I wanted to know how many moles were in 0.095 grams of sodium chloride, I guess I should have had this appear one at a time. I would first find the molar weight of sodium chloride. So I'd add 22.99 for the sodium, 35.45 for the chlorine, and have this molar mass. So that was something similar to what I asked you on your test. And then if I wanted to find the moles, then I would take this mass, 0.095 grams, so that would be just like a sprinkle of salt, and divide it by the 58.44, and that would give me this number of moles. All right, I think I have one. Oh, nope, that's the end of it. I thought I had one for you guys to try. Okay, so we're going to stop this one. Put that so y'all can see it. And we are going to go to solutions. So this is the next part of your guided notes. Okay, so you probably at some point in your childhood had something like Kool-Aid. Maybe it was fruit punch, maybe it was Hi-C, whatever. If you filled your cup with ice and then had your fruit punch in there and then let it melt, it probably looked paler in color. So we can change how concentrated something is by adding water to it. So the diluted has less of it, the concentrated has more of it. So it's a ratio then of how much of the stuff, in this case, our drink, versus how much of the solvent. So the solvent is usually water, the thing we're dissolving it in. And the stuff is what we call the solute. So the solute is the thing we're trying to dissolve, usually like a powder or like fruit drink powder or something like that. Maybe it might be salt. And the solvent is the one with, is the water. So we can think of this kind of on the particle level. So back here, this is our macroscopic domain. And this is our particle domain, imagining these as particles. So if we just look at the top part and compare the concentrations, if we have all the same volume, but different numbers of particles, which one of these is most concentrated, A, B, or C? A is most concentrated, right? Now it's a little bit harder to tell when we change the volume. So if we have this down here versus this up here, it's kind of hard to tell what's going on. But if you have the same number of particles and different volumes, so look at C here and E, they both have 3 particles, but this one has less water. So imagine that those particles were what was making our drink red. Which do you think would be darker? E or C?
E.
Well, that wasn't what a choice. So C up here or E? Oh, you said E. I thought you said B. I was like, B is over here. Yeah, E would be darker, right? Okay, so if I have less water, then it's more concentrated, okay? So more water is more dilute, less water is more concentrated. Okay. So concentration is how much solute, that's the stuff, is dissolved in the mixture. And let's see, we haven't gotten to the formula for molarity yet. We're getting there. We can measure it in a few different ways. One way is percent by mass. So this is where we just say, what's the mass of the stuff? Say sugar. What's the mass of the whole thing? And what's our percent? Okay, so we can do that by masses. A lot of times things at the grocery store are measured that way, like vinegar is measured as a mass percent. We also can do volume percent. This is usually done when we have 2 liquids instead of a solid and a liquid. So if you ever buy rubbing alcohol in the pharmacy section, you can get 70%, you can get 90%, and that's by volume. That's where they said, let's take 700 milliliters of this and 300 milliliters of this and mix them all together. But what we're interested in chemistry is this one, and this is what you're going to write for number 3. Molarity is moles of solute divided by liters of solution. So 1 liter is 1,000 milliliters. So milli means 1,000. So a millennium is 1,000 years. And most of the time when we're measuring things that we would either cook with or drink, or, you know, even if you're buying a soda, if you look at the measurements, that's in milliliters. Even if it's over 1,000, it's usually in milliliters rather than in liters. So you have to kind of do a little bit of finagling with the numbers to get what you want. All right, so as I said, vinegar is usually done as a mass percent. So it's a 5% solution. And if you zoomed in down here, it would say 5%. So if there are 25 grams of acetic acid, that's the chemical that makes it vinegar, in a 500 gram solution, then we would take our 25 grams, that goes on top, the smaller number is the part, and then the bottom is the whole, 500 grams goes on the bottom, 25 divided by 500, and then when you do percents, you got to multiply by 100, otherwise you end up with a decimal. and you would get 5%. So if you were at the factory, you might take 25 grams of the acetic acid. When it's pure, they call it glacial acetic acid. I don't know why it's not cold, but they call it glacial acetic acid. And then you would mix it with 500 grams of vinegar. All right, let's do a percent calculation. If I have 250 milliliters of syrup, and I made this syrup by dissolving 135 grams of sugar in water, and the mass of the whole solution is 300 grams, I want to know the mass percent. What would I do? Well, my solute, the smaller number, goes on the top of the fraction, 135. My solution, which is everything, the whole, goes on the bottom. The 135 divided by 300. You might try plugging that into the calculator, make sure I did the math right. Now, if you just do 135 divided by 300, you're going to end up with 0.45. So to turn it into a percent, we got to move that decimal over to or multiply by 100. Well, oh, that's right. For some reason, I have like 5 of this particular slide. I don't know why. Okay. What if I wanted to find the molarity? So this is the one that's on your paper. Okay. So this one, instead of using grams, I'm going to use the volume. So we have 275 milliliters. So that we got to change into liters. And then we have 135 grams of the sugar, and we need to change that to moles. So for number 4, this would be a good one to write down. We're going to do the calculation for molarity. Okay. So first we need to find the molar weight of the solute. Did this before, but that's what the calculation would look like. So we're just adding up the mass of the 12 carbons, the 22 hydrogens, and the 11 oxygens. I'm so sorry there. I didn't realize that screen had gone off. Hopefully you can see now. All right, so from that, we need to find moles. That's this calculation here. So to find moles, we're going to take that mass, the 135, and divide it by the molar weight, which is the 342. Okay, so do 135 divided by 342.3. So the next slide is going to make what's on this slide small. It's still going to be there, but it's going to be smaller so we can fit everything on the same slide. Oh, maybe not. I did fit this one on this one. Okay, so it's a good idea. If you're not going to do it now, try it later. Make sure you get the same number when you plug things into the calculator, because a lot of times when people are doing the math, the problem they have is with plugging things into the calculator. So make sure you're consistently getting the right numbers. All right, so now the stuff that we had before, it's still there, it's just smaller. So to find our concentration, we have to put our volume in liters. Okay, so we had 275 milliliters, and here I just said it was 0.275 liters, but how did I get that? To go from milliliters to liters, we divide by 1,000. So that's why I said there's 1,000 milliliters in a liter. So we're going to take that 275 milliliters divided by 1,000 milliliters per liter. And that's what gives us 0.275. In chemistry, we are almost always moving that decimal 3 places. The only time we move it 2 places is for percents, but every other time when we're going milliliters to liters or grams to kilograms, it's going to go back and forth 3 places. And we're usually trying to get closer to the number 1. So if we're in the hundreds, we're going to make it smaller. But if we have like 0.00 something, we'll go in the other direction. Okay. So 0.275 liters. Milliliters cancel out. Right. And then for our final step of the calculation, we put those together. The 0.394 moles divided by the 0.275 liters. And that gives us 1.43 moles per liter. So for most things, if you were in the chemistry lab, you would probably have molarities that would be like 0.1, maybe 0.05, up to about 1 or 2. That's pretty typical for working in the lab. But sugar is really, really soluble. So when we do the molarity of sugar, we can get really, really high molarities. We can get concentrations of 6, 10, 15 molar because sugar is so soluble. All right.